me see if share my screen. Okay, do you guys see my screen? Are you ready? Awesome. Okay, so this is the last topic, literally the last topic, and then we practice. Right, obviously last topic would be the most difficult, but I told you it's just due to a lot of mathematics in it. But yeah, it's just steps that you take. It's also just an algorithm, and yeah, then it's the last topic. That's interesting. But let's get to it. Okay, so your last algorithm that we have is the steepest ascent or descent algorithm. We also call it a multidimensional gradient method. Multidimensional due to the fact that you've got more than one variable. Remember, if you have only one variable, you'll use the golden section search method or algorithm, and you'll work with that one variable with intervals for that one variable. So when we had x1 and x2, it was referring to the same x-axis, just different positions or coordinates or interval values. Whereas this method is having a x and a y axis, or an x1 and an x2 axis. So two different axes or more, multi-dimensional. Right. Sorry. So looking at this picture, I just wanted to give you like a kind of an introduction to how it works. So it is a search method, and you'll be starting somewhere on this plane, and you'll work your way to the objective, which is either max or a min. So the starting area is literally an initial guess. So you could substitute the first coordinate into your function and see the value that you start with or the position that you start with. But then what happens after that is, so where you start, you would be checking what is the gradient at that starting point. So if the gradient is negative, you know that it's following a downwards or descent route if you're going to go from that coordinate. So if you want a minimum, then that's perfectly fine. If you wanted a maximum, you'll then try a different initial path or initial value to see if you can rather have an upwards or an ascent, a gradient, so a positive gradient. In this case, I'll focus on quickly explaining what would happen if it was a min problem. So if it was a min problem, you would see, okay, the gradient is actually negative, so it's going downwards. Then what's going to happen is you're going to actually work with vectors. So vectors meaning you have two directions or three directions depending on how many variables you do have. So if you have two variables, then you'll have an I and a j, meaning you'll be able to move on the x-axis as well as the y-axis. So don't make it complicated. It's just saying how it moves. Remember, vectors is moving with direction, right? So those values would give you the direction that you're going to. So you'll then get this vector that will tell you, okay, what direction can you be moving in with that position, right? And that gradient. So with that gradient, you'll be able to move. And then you're going to have some certain step size, meaning how far will you be able to move before the gradient changes again. So usually with a function, the closer you get to the minimum, the steeper it would be, or the higher you climb a mountain, the steeper it would be to the top. So the smaller steps you would take before the gradient changes again. So every time the gradient changes, you'll be having a new coordinate and calculate a new gradient and the new vector to see where are we moving next. Then again, you'll have a step size to say, but how far can we go before our gradient changes again? And then you calculate the new position, new vector, step size, and so every time it's a step that's being taken. And eventually, you'll see it gets very smaller step size. You get smaller and smaller step sizes, and then you're gonna eventually meet your minimum. Right, so that's the idea. That's how it works. But obviously, now we get to the actual calculations, how to get it to work. So you have to remember the fact that if you want a minimum, you want your gradient to be negative. If you want a maximum, you want your gradient to be positive until you get a gradient of, who can guess what the gradient should be when I'm at my minimum or my maximum? What should the gradient be? 0, 0, 0, 0. Remember an extreme point. If you find your gradient, but first, obviously, your first derivative, meaning find your gradient, then if it's equals to 0, then you know you're at an extreme point. So one of your checks would be, if my gradient is literally 0, it means I met an extreme point, either a max or a min. But it could also mean that I found it if my direction changes. So meaning, if I've been climbing downhill and then all of a sudden I'm climbing uphill, so if I had negative gradient and now all of a sudden I got a positive gradient, it means I already met that minimum. I'm just taking a step size past it. So I already met it and I can actually conclude what the value would be close to get that minimum. Right, so as soon as it changes direction, so for example, you'll be going down, 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 and all of a sudden it goes up. Now you know, oh, okay, I probably already met my minimum. If you go up, 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 and all of a sudden you go down, then probably I met my max. But the only tricky part with that is you'll actually continue searching. For our scope, we'll stop searching, but technically you'll continue searching because what if it looked something like this? So you'll be having a saddle point maybe that you think, oh, I reached my maximum, and then actually it goes up even more. So if you then continue to search, you would have seen eventually your gradient would go even further upwards. Then you would know, okay, up, up, so not really a maximum, but a saddle point. But that's why we have that Hessian matrix to help us check if it's a saddle point or not. Right, so checking here, I've gave you a few tips there. So basically what you're doing with this multivariable search or steepest ascent or a descent is you're breaking it down into single variable problems. So if you want to, I'm not going to show you how, but if you want to and you get to a stage where it's a single variable, you'll be able to use the golden section search. I'm not saying you have to, I'm just saying it's a possibility, right? But it is following a path to the ascent, or if you want a maximum, so you're increasing, or you'll be able to following a path. Apologies, this should say minimum. I'll just fix this later. So the minimum, because you're decreasing, you want to find a minimum. So it's either going ascent or descent. So you're following a path ascending, and the more steeper it gets, the closer you're at the maximum. If you descend, then the steeper it gets, the closer you are getting to your minimum. So that's the idea. I have to just make a note that I have to go change that. Right. Okay, so that's the idea. Let's see how it works. So here's some steps to help you. So you can start from initial guessing point. You could have used your Hessian matrix to help you determine whether that point is a good point to use, meaning it's not a saddle point, for example. And you can check whether it's concave or convex close to that point, and then have some kind of indication on, are you going downwards or upwards? However, we have an initial guess. That's basically the point. Initial guess, and we start looking from that guess. Right, now at that guess, so from your initial guess, you're going to start looking for your optimal solution. So you'll first need to find the gradient so that you know, is it going to go upwards or downwards, depending on what you want. So if you want a max, you want it to go upwards or positive. If you want a min, you want it to go downwards. If that doesn't work, you'll usually choose a different initial guess. Then you have to calculate. So you'll just see, before I say that, what you have to calculate next, you'll see we normally denote the gradient of a function with upside down delta of that function to represent that this is now the gradient of the function. Now, after that, after you have the gradient, you can calculate the step size with the, well, what we call a vector. So you're going to calculate your step size. We denote it with an H there. And that will give us direction to know where are we able to move, right? So you could have used then the golden section algorithm or our method that we will be using. After that, when you get your step size, you're actually going to substitute it back, meaning I know where to we can move before our gradient changes. So when I substitute back, we actually take that step. So we substitute it back to actually take that step. Right. I see someone asking about the project. The due date is still the 10th. It's just the cutoff date is extended. So you'll be able to submit after the due date. And you're allowed to. It's just because there are a few students that don't have enough group members. So we technically extended it just for those. So if you need it, use it. Right. It's a pleasure. Right. Have here. So we substitute back. We find a new coordinate, meaning you take a step. Right. You take a step to a new coordinate. And then once you're at this new coordinate, you repeat the process because you're going to keep on moving until you find your min or your max. Right. When the step size, just a note here, when the step size changes direction, you can assume that you were at a minimum or maximum. Like I explained, if you went down, you all of a sudden go up, you can kind of assume that you already reached the minimum. If you went up and you all of a sudden go down, you can assume you already met a maximum. You can't for certain say it was the global min or the global max, so technically you'll continue searching, but for our scope, we will stop and say we found one, a local one, right? Then the same applies. I told you if your gradient is going to be 0 at a point, you know you met an extreme point. Technically, you'll still continue searching to make sure it's not a saddle point, but in our scope, we'll then stop and say, oh, okay, we found a max or a min and we're done. Right, so take this note to heart. Now let's see, how does it actually work? So first off, you have to remember the fact that to get that gradient, in order to check if it's going to be 0, to get a gradient, you have to find the first derivative. Right, so because we're working with more than one variable, you'll still be working with partial derivatives like you learned yesterday. Right, so it's again still partial derivatives that we're working with. Right, so that's going to be a bit of a recap, but not so deep because we don't do the second derivative, because the second derivative is more specifically for checking what is the overall gradient. Right, to check the if it's concave or convex. So here we stop at the first derivative because we want just the gradient. We don't want to check. We just want the gradient, and then we want to move. Right. So we're going to use an initial guess. So you'll see there we're using our initial vector guess where it is normally written as a matrix, right? Where it's normally a matrix written in terms of x and y, or x1 and x2. So you can write it as x1 and x2. And then the coordinates will fit to x and y, or x1 and x2. All right, so this is our initial estimate, so our initial guess. So usually in the test, we will give you the initial guess. Otherwise, everyone can start anywhere, so that would be quite chaotic. All right, so we will give you an initial guess to work with. So our initial guess is 2 and 1. All right. I see someone asking about the updated date. It's on a Friday, the week after Friday. Can't remember the exact date. I think it's, I don't know, 16. Ah, thank you, Henry and Brandon, 16. So it's just a few days extra. Okay. All right. Yeah, that's all. Right. Okay, so step number 1. So guys, for this, we need to first check what is happening to our z value, so our function value. So what you're first going to do before you do anything else is you're going to substitute these coordinates into your function itself. So you'll see there, into your function itself, to check what is the value. Now, the reason I do this is we want to know what happens to our z value. So if you are looking for a minimum, then you want this z value to decrease. If you're looking for a maximum, you want this z value to increase. So it's kind of an easier way to check if you are actually following the correct path. Right. So we can specify what you should search for, or you might need to use the Hessian matrix to figure out if there's a min or a max, and you can then search for whatever you found, what answer you found. Right, but like I told you yesterday, be careful. We can have a function with multiple minimums, multiple maximums. So I can ask you to do the Hessian matrix, and then afterwards I tell you, determine the minimum from this initial guess. It doesn't mean that your previous answer was wrong if you had a maximum. You could have just had a point that was going in a direction of a local maximum. So don't go and change your previous answer just because this time I'm asking for a minimum. Right, it could have multiple. Please be careful. Right, so we substitute. How do we substitute? Okay, so we have a function there. So you're literally going to substitute x into x and y into y, or x1 into x1 and x2 into x2. So there we have a function in terms of x and y. You literally take your coordinate of 2 and 1, and you're going to substitute that in. Right, so in x squared, you substitute the value of x, which is 2, that's square, into y squared, I substitute the value of y, then 2 times x plus 4. So if you substitute that, you're literally saying f of 2 and 1. All right, so 2 squared, 4 plus 1 plus 4 plus 4 is 13. So that's our starting value. I'll go back to the journal very soon. Now we have to calculate the gradient. So the gradient, you need differentiation to calculate the gradient. Now, because you've got multiple variables, you have to use partial derivatives. Okay, so we go back here. Partial derivatives, right? So f of x and y is equals to x squared plus y squared plus 2x plus 4. So now I'm going to do our partial derivatives. You'll see there you can say df dx, or it's the same as saying the first derivative in terms of x. So we're going to focus on x. So let's see. Focusing on x, you'll see your first term does have an x. So when we derive that, multiply the power in front and subtract 1 from the power. Now, there's a plus separating the terms, so this is a separate term. What happens with this y? From yesterday's work, what happens to that y? The y square. Zero, perfect. It falls away, perfect. We see it as a constant because it doesn't have an x, so that just becomes plus 0. Then the next one, next term is 2x, so we have to derive that. Be careful. A lot of people would have skipped that. It still has an x, so it doesn't fall away. So 2x, you go and actually derive that, just becomes 2. If you wanted to write it out, x to the power of 0. 1 times in front, it's 2, and subtract 1 from the power, it becomes 0. Then another constant value, that one just falls away. So our first derivative in terms of x is 2x plus 2. Now we have to do the same for our other variables. We only have another variable, which is y. So we now go and say the first derivative, but in terms of y. So we're going to work now in terms of y. So we go and we say, same function. We're not doing yx or xy. It's still the same function we're looking at, but now in terms of y. So our first term is separate, doesn't have a y, so we see it as a constant. Our next term has a y, so we can derive that. So it becomes plus 2y to the power of 1. The next term, no y, no y. So you've got 2 constants. That falls away. So that would leave us with just 2y. Right, so that's how we got these values from. Now we actually have the gradient of the function, and we need to actually take this point and evaluate the actual gradient, meaning what direction can you move from this specific point. So you have your gradient for your function, and you want to check at that point what's the gradient for that specific coordinate. So you now literally substitute your coordinate into this. Our coordinate was 2 and 1. So now we go and we say, okay, we're still using the same 2 and 1, and we're going to substitute that in. So into our first one, I normally write here an I or something just to represent that that's our first vector value. Don't say x, because remember, if you say something like 2x, you still need to solve x, but we're substituting something into x. So you have it. Right, so no, we're using different variables then. I and j, just representing a vector where 1 is on the x-axis moving and j is on the y-axis moving. Right, so we go and we say, okay, that would be for our x-axis. So we're looking at it in terms of the x-axis. So in terms of x, f derivative in terms of x. So there we're going to use our first derivative in terms of x. But it doesn't mean you'll only have an x to substitute. You might have a y inside as well. You have both x and y, 2 and 1 there. Right, so x is a value of 2, so we substitute, so that's going to give us 4 plus 2 is 6. I almost said 6 plus 2 because of the answer. But that's 6i, representing on the x-axis. If you don't say I, I'm not going to know that this is the x-axis. So 6 on the x-axis, it moves by a positive 6. You don't have to write the plus, but it helps us indicate that that one moves in a positive direction, whereas negative would have been the opposite way. I'm not saying the gradient is positive. I'm just saying that on the x-axis, it moves in a positive direction instead of a negative direction. So to make it clear, if I had a vector starting at this point, let's 2 dimensions. I'm not going to look at it in more dimensions right now. So if I had y equals x squared, so just 2 dimensions there, and I would substitute something. What would happen is if I would have gotten this I value, it would have told me that it moves positive 6 on the x-axis. So from whatever initial guess I have, in this case 2 and 1, it would move positive on x. So positive is in that direction because that's going into the positive side of x. Remember your 0, negative 1, 1, 2, 3, it goes into the positive direction. So you'll be moving 1, 2, 3, 4, 5, 6. But that's not the complete vector. You need both variables. So then you'll have maybe, let's calculate it. So for your j, you'll then say f of y, and you'll substitute whatever values you need to. In this case, we need to substitute y, so that's a 1. So that's going to give us a 2j, telling us positive 2 on the y-axis. So on the y-axis, you'll have negative 1, negative 2, blah, 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 going downwards, but upwards, you're going into a positive direction. So we go positive 2, meaning it's climbing 2 units upwards. So where they meet, you can actually see your vector, which gives you the direction, right? So it goes from that point to the next point. So it gives you your vector in terms of giving you a direction to go to. Right, so it tells you which way, so to speak. Okay, so let's see. We've got now these two, 6 and j. So just to explain, where does that I and that j comes from? So you'll normally then write here 6i and 2j to specifically represent that this is on the x-axis, and this would be then on the y-axis. It could have been x1 and x2. It really doesn't matter. It's just different axes. Right, so we've got now our vector in terms of our gradient. Now the next step is to actually write out your vector. So now you can say I've got my gradient in terms of my function. Remember, the upside down delta refers to our gradient for that specific coordinate. So that is now in terms of your x-axis, how does it move? And in terms of your y-axis, how does it move? You can have more axes. I'm just saying this is for this specific example. All right, so you can even have a k, I, j, k, l, m, depending on how many variables you have. All right, but it tells you the direction. Now we can go on. So please, guys, don't write to me 6x plus 2y, because then you're telling me we still need to find x and y. We do have the direction. We already have our answer for x and y. Please don't do that, right? That means something else. Right, now we're going to say, okay, we're going to move. Right, so we're going to have to calculate our step size. So we need to be able to know how far will it move before the gradient changes. Right, so you'll see there we talk about I plus 1, meaning our initial guessing point plus 1. So we wanted to actually move a step, one step. Okay, we can't skip steps. So it's just the first step. So in the first step, to get the first step to move, you first need the initial actual step to know where we're moving from. You need the step size to know how far will it move. And then you need to be able to say, okay, but in terms of moving, we still need to multiply that step size with the gradient of that specific coordinate, because otherwise you're going to move in the wrong direction. Right. So please don't forget the actual gradient, because that gives you direction. The step just tells you how far, but the gradient will tell you which direction. Right, so that's a little bit of a formula you need to remember. Right, so initial, so whatever step you are currently at, in this case it's initial, whatever step you're currently at, if you are at step 2 already, then you'll say I plus 2, and then here, so the vector of I plus 2, so here it won't be now initial, it will be initial plus 1, because you would have had your previous step. So every time you build on the next step, because you're moving onwards and onwards, you're not going to move from the initial step every time. I mean, you moved, so you need to move from the next one. Plus h still, and then the specific gradient and step from that specific coordinate or position. If you went on further, you would then go and say +3 there. I'm taking my third step. Whereas this step would go from the second one and with its own step size and its own gradient. Right, so just showing you that it changes based off of which step are you going from. Okay, so we don't know the step size, we have to calculate the step size. So we now first substitute what we do have. So you'll see here, we do have our initial. So let me just do this. So we do have our initial step. That was the 2 and the 1 that we had before. I just tend to write it like this to not confuse which one is for x and which one's for y. So the top would be your x, the bottom would be your y. Plus h, because we do not know what h is yet, but we do know the gradient. The gradient was 6i plus 2j. I is in terms of x, so 6 on top. 2 is in terms of y, so at the bottom. You always write it in terms of x, y, z, blah, 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 blah. Right. So we can go and add our terms or multiply and add our terms. So from that step, what's happening? Let me show you what's happening from that step. So from that step, we're basically saying we first multiply the h in. So it becomes 6h and 2h. Remember, it's like expansion of brackets. So if you wanted to write it like this as well, you are more than welcome. It's just confusing because then you have to say 6i and j, and then you're going to be including i's and j's, and that's not it. I just represents the x value. You don't want x and y in there because then you have more variables than you need to solve. You only have to solve h, not x and y. But yeah, FOIL, you'll go and multiply that into both. So that's all that happens first. And then we just say basically that these are for x, so they get put together, so almost like terms. And these are for y. So that's how we get the 2 plus 6h for my x variable and 1 plus 2h for my y variable. So that's how that gets calculated, or just added together technically. Right. So that's that step. Now, the hard part. So in this hard part, we actually have to substitute this into our function in order to solve h. Now, what's going to happen is you're going to substitute this into your original function every time because the function does not change. So you substitute x, the top, into x, and the bottom y into y. After you can sort it out, unless if you want to immediately derive, you're going to find the derivative. So recap, if I find the derivative of something, let's say I found the derivative of h of h, I'm just saying a function in terms of h. If I find that derivative and I set it equals to 0, I'll be able to find the maximum. In this case, we're finding the maximum. H is the step size. So you're finding the maximum step size that it can take before changing direction. So setting it equals 0 finds the extreme max. And what are we doing? We're finding the max step size. So you first have to find the derivative and then set it equals to 0 to find that max step size. So you'll see here that when we substitute it in, what I do is I first go and sort this out by multiplying, simplifying, adding like terms, and then I give it a new name in terms of the function because it's not in terms of x and y anymore. It's now a new function we create, which you technically can do the golden section search with, int, one variable, right? But it's in terms of h. And you can then derive that, and you can say, okay, take this, find this. Right, you're not deriving the original function, you're deriving the function in terms of h, so I give it a new name, g. Okay, now you can decide if you're comfortable with, for example, the chain rule. You can decide to, from this step, to immediately go and derive, if you're comfortable with it. Plus and a minus is just a sum or difference rule for differentiation, meaning you take them separately. This is going to be chain rule, this is going to be even chain rule, and then this is just a constant that would fall away. But it is tricky to do, so make sure you try it before a test and check if you get the same answer there for your first derivative, which is actually on the next page there. Right, but we're going to do the long way to avoid teaching you all of that from the beginning. So what's a long way which has been embedded in your brain? That is FOIL, right, or normal algebra. So you're going to expand your brackets and then add like terms. Right, so let's see. So let me go here and say, remember our function originally in terms of x and y was x squared plus y squared plus 2x plus 4. I'm just going to open that like this. Into x, I substitute that. And into y, I substitute that. So you're literally going to go and substitute those in there. Normally, we would go and say it's 2 plus 6h, and that's going to be 1 plus 2h for the y value that we're substituting. I'm just going to write it here at the bottom. So x squared, so 2 plus 6h squared, plus y squared, so 1 plus 2h squared, plus 2 times x, 2 plus 6h, and plus 4. So if you now go and you multiply, remember square does not mean you just square everything inside, unless if it's by multiplication. If you had 6h on its own and you square that, then it's going to become 6 square h square. And then obviously you can make that 36. So that would be perfect because it's multiplication in the middle. But as soon as there's a plus or a minus in the middle of terms, you cannot just do that, please. So I'm going to do this quickly and say, this is not that, right? It is 2 brackets. So you'll go and say that's going to become literally this. The next one is going to become this. The next one I can immediately go and multiply in. Right, so that's going to become plus 4 plus 12h, and don't forget the 4 there at the end. Right, so we're ready to start with our long brackets expansion. So normally we just ask for the final answer. So whether you did chain rule to get the derivative or not, it's perfectly fine. So we go this one, this one, this one, and this one. Okay, quickly give me the answer for that expansion while I do it. See if we match. Give me the answer for that expansion. Let's see who's quick. 4, yeah, I agree with 4. 6h times 2 is going to give you 12h. I'll write it out for those who are doing it step by step. 12, and then you're going to have another 12h. And then lastly, you're going to have a 36h squared. And then you add your like terms. So I agree with your answers, 100%. Very good. So that's just for that bracket. Right, now let me do the next bracket. So that's going to be this one, this one, this one, this one. You can try and give me that answer. What's the answer for that one? So 1 times 1, that's a 1 there, yeah. And then you're going to have your 2h times 1 and your 2h times 1 and 2h times 2h. That becomes 4h to the power of 2. We add unlike terms. So 1 plus 4h plus 4h squared. Perfect. Very well done. You guys got it. Right, just remember if you multiply an h and an h, you add the powers. If you add an h and an h, you just add the coefficients, right? So that one was for that. Then we shouldn't forget our plus 4, plus 12h, plus 4. All right, so let me just write this out. So right now we currently have all of this. We have all of this. We have a plus 4, which you could have already added with the other 4 there. Plus 12h, plus 4. Let's add our like terms. So you'll see the constant. Now, guys, just to give you a hint, you're going to derive. So if you don't have time, because we normally use a lot of small numbers, so you'll be working with fractions most likely. So if you don't have time, what happens when you derive? What happens to a constant? What happens to a constant when you derive? 0 falls away. So even if there's a block but you don't have time right now, write it on paper so that you can come back and quickly calculate, but know that it's going to fall away anyway. So continue and then later on maybe come back. It's not going to be 5 marks that you lose if you don't have time, right? Because we know it falls away. I'm not saying you shouldn't calculate it because we'll probably ask you for the answers. But yeah, it falls away. So anyway, it's just so that if we wanted you to do golden section search, then that value would have been important because then you don't derive at all. Okay. Right, but let's see. What is 4 plus 4 plus 4 plus 1? 13. Is that correct? Yes, no, maybe, could be. Is that correct? Thank you, Christian. Then our next value is all the h's to the power of 1. Is that 40h? Is that correct? That was a positive 13, sorry. You happy with that one? Awesome. Then the h squared, so that's just going to be also 40. H squared. And then we have our final answer in terms of G of H. So you could have now gone and do the golden section search. All right. Yeah, sure, Kenneth. I just don't know how far to zoom out, so I'll go like this. Is that okay? Awesome. So you could have now gone and done the golden section search of this new function that you have. Right, but we're going to continue with our normal steepest ascent or descent method. So we are still trying to find the minimum, so we're hopefully going to go down. But let's see. So we want to take the max step size. So remember taking the max h or step size. We take that derivative in terms of h, and we set it equals to 0 to take the max or the extreme. Right. So here we go, and we say, okay, we need to then find the derivative. So now the derivative is easy. You already know how to work with the power rule and separate terms. Separate terms, meaning they get done separately. That's just a sum or difference rule. It's just one variable, so you don't have to worry about partial derivatives. It's simply just saying everything is in terms of h, so I simply just go and derive everything. So 2 times 40 gives me an 80, subtract 1 from the power. 1 times 40 gives me still positive 40, subtract 1 from the power. A constant falls away. So now we're going to say our first derivative is then just 80h plus 40, and we want to set that equals to 0 to take the maximum step size. Can we solve h? What is h? Evan is on a roll day today. Or Evan. Sorry if I pronounced that wrong. I see him typing and I'm like, oh, okay, he's gonna, but Henry beat you to it. Okay, Henry, half. There we go, Evan. There we go, Kenneth. Okay, cool. Let's see. Henry, that's much better. Awesome. So we go and we say, okay, take one of them to the other side. It becomes the opposite side. Divide by 80 both sides. And then your h is going to be, you literally use your calculator. Don't go and punish yourself. Type in negative 40 over 80 so that you can get the simplified answer. It's minus 1 over 2. Right. Yeah, you were like, should I press enter? That's so classic. But okay, so right now we have a step size. So if we have a step size, we can actually move. Okay, now just one thing there, guys. Please use your calculator. Don't try and do things in your head. The fractions will get quite small, and then you're saving yourself some punishment. Work with fractions. I hope you heard me say that. Work with fractions. Do not write it as decimals. Those decimals will start looking crazy, right? Because you're going steeper and steeper, and those decimals will get smaller and smaller and smaller. Right, so please work with fractions. It's only if we ask you to fill in, then you fill in, obviously. So my tip for the golden section search and the steepest ascent or descent is always to follow an assessment queue, how many iterations they want you to fill in, and then obviously complete it if you can. But follow, but don't type in. Meaning, do it, write it out, to work on Excel, do it step by step until you're done. Then you go to Excel, assessment queue, and then you fill in whatever we ask. So if you've been working with fractions, then you just go and convert it to decimals if we asked you decimal places. But here I'm going to remind you, significant figures are going to be extremely important because you're going to work with a lot of fractions. We don't have right now, but eventually it's going to become fractions, not for this example, but for other examples. So if you have something like 0.0009, and I asked decimal places and some of the values were actually something like 1, 2, 3, that would be meaningful if I said 3 decimal places. But this would be just 0.000. Does not help me at all. Right, so please make sure you can round to significant figures for these, especially. Right, then another tip that I saw and I forgot to mention yesterday. Guys, if you're doing the golden section search, on Excel, I'm not sure where to do the settings, but sometimes when you use the rounding feature there, it does not round like we normally round. I think it always rounds up or something like that. So you have to use the correct function, meaning rounding function that would round like we should. So if it's 0.5 and above, it rounds up. If it's below, it rounds down. Be careful for that. I saw people losing marks because they just purely got on Excel and rounded on Excel, and then they're like a point off. And here we want accuracy, so that was marked wrong. So please double check when you use the rounding in Excel, or if you have your answers first, make sure your columns are wide enough to see that they're not bigger, and then you round it and you make sure it matches to what Excel is rounding. Okay, do not take chances. Please don't take chances. So I'm just giving you some advice because I've seen a lot of wrong answers just due to the rounding differences. Right, so if you're fine with Excel, do it. But of course, if you're not sure, double check. Please double check always. But on Excel, make your cells bigger so that you can see the actual places after it rounded, so that you can make sure it rounds correctly. Right, if it doesn't, you round. Okay. It depends on the question. So if we say you can put in a fraction, then it will allow it. But if we say round, then sorry, then you have to put it in as decimals. So that's why I'm giving that advice. If we ask you to round, then do it as fractions when you calculate, but then when you fill it on assessment queue, only then you write it as a decimal and you round. Right, but if we say fractions, then you stick to fractions, save you some effort there. One more thing though, some decimal values will be so small that your calculator is going to probably say, can't put it into fraction because I do not know how. I don't have sufficient memory to do that. Or something like that. Or it's just so small, there's no fractional form. In that case, we'll definitely say if there's no fraction, then you should round to this and this and this. Right, because yeah, it doesn't always give fractions if the values are extremely small. So in that case, you'll have to, it doesn't matter if we allow fractions, you'll have to know how to round significant figures. Right, so please make sure you do that. Okay, but we do have our step size. We smile because we can now move to the next coordinate. So we're now going to move to the next coordinate. We're going to take a step. Right, so you'll see here we have our new function. You could have done golden section search, or like we do, we take the function, we get the derivative, we set it equals to 0. Then we get our step h. Now we take this h and we substitute it back where we had h, right, in terms of x and y, so that we can get a coordinate in terms of x and y. So you literally substitute it back into your x and y where it was still in terms of h. So you literally substitute that back in there. So now you can get an x and y coordinate, right? So we literally substitute it back to plus 6 times minus half is minus 3. We got 2 minus 3 is negative 1. 1 plus 2 times minus a half is going to be 1 minus 1. It's going to give you 0. So this is your new coordinate. And you moved. That's basically a move. Okay, so now we repeat. Right, so now we repeat. So first things first, we want to see what happened to our function. Right. Now, we substitute this new coordinate into our function itself to see what happened to our function. So you'll see you literally substitute it, so I'll do that as well. So into your function here on top, x is now, instead of the 2 and the 1 we had, it's now negative 1 and 0. So you now literally into x, you substitute, so you probably rewrite it. So we now go back here and we say f of negative 1 and 0. So into x, I substitute negative 1. Into y, I substitute 0. Into x, negative 1 plus 4. And then we calculate. So what is 1 plus nothing minus 2 plus 4? 1 minus 2 is going to give you minus 1 plus 4 is 3. So at this new coordinate, our function is, our z value or our function value is 3. Now, previously at our vector initial, our function of 2 and 1 was equals to 13. Do you think this is better? Remember, we are trying to find a minimum. Do you think we're going in the right direction? Yeah, we're going in the right direction. Right, we want a minimum and it's decreasing. So yeah, we're going in the right direction. Your step size is also negative, so it kind of hints towards that it's most likely going to go downwards. You can't always determine it with your step size because you could have had negatives in your function itself, which will then actually have the opposite effect. So I'm just saying it's a quick check, but it's not necessarily going to tell you whether it goes down or up, but it does give you some hint that you are going downwards if it's negative and upwards if it's positive. Right, so we go and we say, okay, it is getting better. We are minimizing, we're trying to find the min z from 13, it went to 3, so it is decreasing. So we are happy it's decreasing. If it was increasing, then I'll have to start at a different guess, because then it's going to a max instead of a min. Right, but for test purposes, you go on with the guess I gave you. Right, you go on with that and you just show. But hint, hint, something's probably wrong. If it's not doing anything, it can change eventually, but it shouldn't change immediately to see that, for example, I ask you for a min. It shouldn't be finding an upwards route immediately. I'm not saying it won't ever, I'm just saying it's very unlikely. Although it could mean that it goes upwards and then downwards, that's also very possible. So I'm not saying it can't happen. I'm just saying it's quite unlikely. So use it as a helping tip if you go and check your function values and it just goes up and up and up and up and up and up. I told you to do 10 iterations, but it just goes up and up and up and up and up and up and up, and you're looking for a min, then maybe you're doing something wrong. Yeah, I'm not saying definitely, I'm just saying maybe, right? Okay, but let's see what to do from there. So now we repeat our steps. So repeat. So step number 1 was to go and find the gradient at that coordinate, right? So we have to find the gradient at that coordinate. So we do our first partial derivatives. But we don't have to do it again, guys. We do have our first partial derivatives. The function didn't change. It's just a coordinate. So to take you back here, when we did this part, your derivatives didn't change. It's just a coordinate. So the only thing that will change is when you substitute that coordinate. So it won't be 2 and 1 anymore. It will now be -1 and 0. So the first partial derivatives will stay the same. So please don't make a mistake on your first partial derivatives, right? Because that messes up everything. I tend to do it again at every step to make sure that I didn't make a mistake with my partial derivatives in the first one, right? Because maybe my eyes didn't pick it up, and at the second try I realized, whoops, I wrote something wrong. Then I can at least quickly go fix. Right, so just giving you some advice there. So we're still using the same partial derivatives. So your first partial derivative in terms of x was 2x plus 2. Your first partial derivative in terms of y was 2y. What's our new coordinate? It is -1 and 0. So we now substitute this -1 and 0. So to get our I value, we're looking at the first derivative in terms of x. To get your j value, you're looking at the first derivative in terms of y. So in terms of x, we go and substitute into that one. So our x value is now -1, and our y value is 0. So we have then -2 plus 2, h0i, 0j. Who can tell me what's the significance of both being 0? Because this is our gradient of our function. What's the significance of both being 0? Both. Yes. Optimal extreme point. Very good. If they're both 0, it means your gradient is literally 0. Not if one of them is 0. Guys, please be careful. If one of them was an actual value, it just means that on that one axis it doesn't move, but the other axis it does move to get the direction. So please, please, please don't assume if you see 1, 0, you're done. Everything must be 0 before you can say that gradient is 0. Right, please. So all axes or axes, all axis variables must be 0 before you can say the gradient of the function is optimal. Right. Technically, you'll continue searching in real life because this could have been a saddle point. And then you'll see it just goes in the same direction afterwards. But you'll see now it's not as simple as just continuing. If you have a gradient of 0, what is 0 times anything? What is 0 times literally anything? 0. So when we substitute into our calculations, there's a multiplication with our h. Remember, it's that whole x. Now it would have been I plus 2, and I'm coming from our I plus 1 coordinate, and I multiply my h with my gradient. So it's going to multiply with 0, which means even your step size will be 0. So are you then actually stepping if you're adding 0 to your initial step? Well, in this case, our previous step. So it doesn't matter what step is, -1 and 0. If I'm adding 0, I'm not going to move. So in that case, you'll then have to take these coordinates and change them a bit, so meaning move yourself, and then see what happens from that coordinate, right? But for purposes of our course, we're simply going to say, okay, we met our optimal. So we can then go and say, what's our optimal Z? So you could have seen that we calculated it before, where we said f of -1 and 0 was actually 3. So that's our optimal solution. And we're done with this one, of course. So just to show you you would have got your new coordinates, substitute C/3 value, it's better, and now your initial point is this. You do the whole steps again, but because both of them turned out to be 0, you now know that your gradient is actually 0, so optimal solution. Sometimes you might skip the optimal solution and you'll start seeing your Z value doing the opposite. So we actually had our Z value decreasing, and then all of a sudden you might see an increase in your Z. So instead of 3, the next one could have been 4. Then you know, okay, the previous one was probably the most optimal already, because now I'm changing direction. So that could also happen. Remember that note I gave you in the way beginning. Right, time for you to practice. Right, you'll see there I included questions for the Hessian matrix as well to make sure you don't forget about it. Right, so let me just quickly check. There's one of them that's quite long and the other one's a little bit shorter. I just have to remember which one is it. So just give me a second. So let me just compare the questions quickly. Let me see, how long does that one go? And then exercise 2. Okay, so start with the one where it has brackets, so meaning question 3 and 4. So start with those just to get the hang of it first, and then the other two. Sorry, I'm swapping them. It's just because I want you to first get the hang of it. I'll still swap them eventually in the slides as well. But start with 3 and 4, then do 1 and 2 last. Okay, so this is going to take quite a lot of time. So I'm going to give you literally until break, because this takes, for the first try, a lot of time. So I'm going to give you until break, and then after break, I'm going to go through one of these, and then tomorrow I'll go through golden section search exercise, and then the other one of these, just so that we practice before the test, and then I'll just find out about the review of the previous test, if it will be open for us to do. Right. If it will, then I'll go through that as well. If not, we continue practicing until you're ready for the test. Right, so do until break. Do everything at the end, right? Like I'm saying start of that, but do everything. Do until break, and we continue. Haven't I said I'm not opening the assignment? I think I did already. If I haven't, I'm not opening it for review. We are actually going to mark the assignment like normal assignments. It's not a test. Test get open for review, not assignments, right? So an assignment, it's not going to be open for review. We will mark it, right? And then, yeah. Andre, I have also answered that question before. It is due on the 10th. The cutoff is just extended, so you can still submit afterwards. So I won't penalize you if you submit after, but just submit on time, otherwise that's the penalty. I mean, you're already getting extension. Don't extend the extension, that's 0. Right. Okay, but I'm going to leave you to it. I'll obviously be here for you to practice. Just want to go check if there's any messages. All right, but please do this now. Don't take a break now, please. This is one of the hardest ones. You're going to see it gets really tricky, really, really tricky with fractions. Please, please do this now. Okay. Just checking if you guys can hear me. Hello. Thank you. Okay, let's do some. See how it goes. Yeah, I think I'll do the one, question 3 and 4. Show you how you can use the chain rule. If you get it, yay. If you don't, then expansion brackets for you, sadly. Then I'll see how much time is left. But I want you to first continue with question 1 and 2 afterwards. So then we'll rather go to golden obviously tomorrow. All right, so we're going to start with question 3 and 4. Take it from the top, and then I'll show you how to do it with the chain rule instead. But I can show you here already in some of these. So let me get to this step. Let's see if I can erase some stuff, because obviously we're not going to use this again. But I'm simply saying you don't have to multiply brackets out if you can purely just do the chain rule. So I'll show you how to do that. Do this, but chain rule meaning you are immediately deriving without expanding brackets. That's all I'm saying. So we have to get the same derivative answer. Otherwise, something is not okay. So let's see. So let's do that. Oh, that was a plus. Okay. So I just want to show you that you could have done it. So you would still substitute all of this into the original function, whether it has brackets or not, you substitute as is. So you'll see with the other question, like I'll leave it with the brackets. It's easier to just not multiply out in the first place. But this one you substitute in like we already do. Okay, but now, if we were to derive this and we see we have brackets to the power of something, we can use our chain rule. So for this one also, chain rule. To the power of 1, don't waste your time because it doesn't work out necessarily. Yeah, I had some cases where it didn't work out. So just multiply that out and then apply your normal power rule plus constant rule. That's not for all of this. Okay, so let's first quickly multiply it out before we do any derivative. So we still have g of h as a function. So it's still all of that. I haven't done any differentiation yet. It's just saying if I've got something to the power of 1, I immediately multiply that out. So we're going to have a plus 4 and a plus 12h. Be careful for negatives if there's any negatives. Right. Then that's just 4. Now from here on out, we're going to use a chain rule for this one. So I'll show you how it works. Like I said, if you get it, great. If you don't, then, well, go watch videos or expansion of brackets. Right, so how to do the chain rule. So the chain rule, you still work with the power. So the power of 2, you multiply in front. So power of 2, you multiply in front. So you kind of see that inside as just x. Then the inside stays the same. But then you have to multiply with the derivative of the inside. So who can tell me what's the derivative of inside the brackets? What's the derivative of inside the brackets? Yeah, just 6. Just 6. Because if you derive 2 plus 6h, 2 is a constant, that becomes 0. There you multiply the 1 in front, it becomes 6. Subtract 1 from the power, so power 0. So it's just purely 6. Then for the next one, let's try, so I'll just do this so you can see that's for that one. Then for the next one, we go and we say that's a plus in front. Okay, that's going to be for this one. So you take your power, you multiply it in front, so it's plus 2. Then inside bracket stays as is. Subtract 1 from the power. I just forgot to write it there. And then you times with whatever is the derivative of the inside, which is in this case just 2. So just write it there, 1 plus 2h. If you derive that, that becomes a 0, and that becomes a 2. Right, so that's that piece. Then the rest is just simply the power rule and constant. The plus 4 becomes nothing. Plus 12h, you do that whole 1 times in front, it becomes 12. And subtract 1 from the power, that's h to the power of 0. So you can write it if you want to. The other one's just a constant. Now we have the derivative, and we can just make it more simplified. So now you can multiply out your brackets. It's just much smaller brackets to multiply. Right, so let me just do that so it doesn't get confusing there. Right, so we now multiply. So you have 2 times 6. So I would go and say that's 12 there times 2 plus 6h. 2 times positive 2 becomes positive 4. Then there's just a plus 12 left because of this being just 1. Then I can now multiply. So 12 times 2 is going to give me a 24. 12 times 6. I think it was 72. Let me just make sure. Yeah, 72h. That's going to be plus 4, and that's going to be plus 8h, and then the plus 12 there. So it's simply just saying multiply that inside. Right, now we add alike terms. 24 plus 4 plus 12. So that's 28 plus 12 is 40. Then this one and this one. It's going to give you 80h. So that is the derivative. And then you can do the whole set equals to 0. So let's see. There we go. So it's the same as this. Right. So you're more than welcome to use this method if we don't ask you the in-between multiplication or something, which is highly unlikely. Right. So I hope that helps a little bit. If you want to screen grab, let me just scroll up. Then you can maybe screen grab if you wanted to just have it again and try it again. You all still good? Did that help some of you? Okay, cool. I mean, if you do not multiply the derivative of the inside, it changes everything. Hey, you're not going to get the great answer. So be sure you are going to remember. Then it's okay to use this method. All right. If we expect you to derive anything other than algebra, then of course we'll do a formula sheet for those. I think Ms. Payne, if it's maybe you that's unmuted, I'm not sure, sorry.
Sorry, Mrs. Turani. Yeah, it's me going off.
No problem. Yeah, it's annoying if that happens. Okay, so next one. If we take the same route, I'm going to allow you to see how to do it again. But know that if you feel like you're not comfortable with using the chain rule, right, go for it, multiply your brackets, and then derive like we normally do with just the power and constant rule. We'll take the sum of or difference rule as well, but I mean, that's just taking each term on its own. All right, so let's see the next question. So question 3 and 4 is what we'll do now, and then we'll see what we have time for more. So this one, question 3, we're looking at f of x1 and x2, where the function is minus x1 minus 3 to the power of 2 minus x2 minus 2 to the power of 2. We first need it does, otherwise we're disproving it. But let's see. So you could have gone now and multiplied out all the brackets. I am not going to punish myself because I know the chain rule. So I'm going to teach you again the chain rule. So we first do our first derivative in terms of x1. So the reason why I can use a chain rule on this, if you look at your two brackets, this bracket only has x1. This bracket only has x2, which means even if I expand my brackets, everything in here, if I focus on x1, anything with x2 is going to be disregarded if it's a separate, I hope you see that minus, a separate term. Right, so I can immediately go and say, I'm going to disregard that if I look at x1 because it's going to just become 0 anyway because I see it like values, like constants. Right, if you want to multiply it out, please do. I'm just saying that would be easier to do this. If you had x1 and x2 in the same brackets, then sadly, you'll have to multiply it out to see what will have an x1 and what will have both and what will have just the other one. I'm saying this works due to the fact that each bracket only has one variable. And I know that if you multiply out, it's going to purely have that one variable and constants that will disappear at the same time. Right, but if you were to multiply it out, the answer would have been, so I'll just write the answer here on top. It would have been minus x1 squared plus 6x1 minus x2 squared, then plus 4x2 and minus 13. So if you were to multiply it out, that should have been your answer, your starting answer, which is easier to derive. Right, but the multiplication is terrible. So I'm going to focus first on this. Why am I focusing on this? Because I'm specifically looking at deriving x1. And I know anything else separately will be seen as a constant, which just becomes 0 anyway. So everything in there when you multiply. So I can show you if you were to multiply all of that out, you would have still been left with, so I'll just write it like this. You would have had the minus in front, but it would have been x2 times x2, which would have been x2 squared. Then x2 times -2 and another x2 times -2 would have been -2x2 and -2x2. You could have already added them. And then -2 times -2 would be +4. Then you would go and multiply your minus inside, plus, and then plus, let's already make it a 4, +4 and -4. So if you did all of that work, remember if you're deriving in terms of x1, this term only has x2. Just make that 2 clear. So it becomes nothing, it falls away. This term only has x2, so it falls away. This is just a constant, so it falls away. So I hope you see where I'm going with this. It only has x2 in it and a constant, so you're left with x2s and a constant. And if you're deriving in terms of x1, all of them will become 0. So just to make it clear, if you had x2 minus x1, that changes it completely, because then unfortunately you have something in terms of x1 and you will then have to go and multiply brackets. You have no choice, right? No choice. Okay. However, in this case, we do have a choice. It's very nice. We're going to go with that one. So now how do I do the derivative of something like this? So the inside, you get the derivative. So that's going to be just 1. So derivative of the inside is just 1. Then I go and say multiply the power to the front. It becomes -2. Then your brackets stay exactly the same times that derivative of the inside. So your first answer would have been -2 times 1, which is -2, x1 minus 3. Then we multiply that out. So it becomes -2x1 plus 6. So that would have been all of that. All right, I hope you see it's a bit easier that way. Okay, for the other side, you would then go and say, okay, find the first derivative in terms of x2. So the first bracket is just x1. So we know all of that will become just x1s and constants. And if I derive in terms of x2, all of that will fall away. So I'm purely focusing on finding the derivative of minus bracket x2 minus 2 squared. Purely just that. Right, what's the derivative of the inside? It's just 1. Take the 2, multiply it in front, -2 there. The brackets stay the same times that derivative. Right, so it's going to be -2 times x2 minus 2. And then in the end, it's just -2x2 plus, and I hope you see why it's a plus, 4. Remember, you have to multiply the minus as well. So -2 times that and that, -2 times that and that. Right, and then you've got that one as well. So that is for x2, all of this. So I hope you've learned something new that might make life easier. Otherwise, expansion of brackets, you would have gotten that top answer and derive that immediately in terms of x1 and x2, which would have been the same thing. If you derive in terms of x1 and x2, I'll do that quickly here below. Just want to write it out again. I just removed my minus. There we go, minus x1 squared plus 6x. Let me see if I've got it written down so that I can just copy. Minus x2 squared plus 4x2 minus 13. So if you derive in terms of x1, you'll see, okay, I'm focusing on x1. That's my first term for x1, so I can derive. So that becomes minus 2x1 to the power of 1, because you subtract 1 from the power, multiply in front. The next one, you check, oh, the next term also has an x1, so yes, that becomes plus 6. You can write x1 to the power 0, but that just becomes x6. Then the next term does not have an x1, so we see it as a constant. It falls away. The next one does not have an x1. The next one is just a constant, a constant, a constant. So it's plus 0, plus 0, plus 0. So you're left with minus 2x1 plus 6, which is the same thing. For the next one, you'll do the same. I'll just rewrite it. Let's see, f of x2. So now you check again. First term is not x2, so it's a constant. They're separated by pluses or minuses, right? Next term plus, so next term not x2, so see it as a constant. Next term, there's an x2, so I have to derive that. We derive by saying take the power, multiply in front, it becomes minus 2, and then subtract 1 from the power, so it becomes a 1. Next one does have x2, so yes, we have to go with it. How do I derive that? Take the power, multiply in front, it becomes plus 4, and then subtract 1 from the power, so it's just x2 to the power of 0, which is just 1. The next is just a constant. So we're left with minus 2x squared plus 4. Minus 2x2-ish plus 4. Oh, it's right above us, right there. So it's the same thing. Right, so that would have been your first derivatives, which you'll also use when you start solving with the steepest ascent or descent. But they asked first for question 3 for the Hessian matrix. So the Hessian matrix, you had to do second derivative. So we had to do that whole first derivative, x1, and then second derivative. Now we look at x1, x1, then x1, x2, then x2, x1, and then x2, x2. Right, so let's see how to do that. So if I'm specifically focusing on x1, then I first check which one was derived first. So it was first x1, so it comes from that one. This one as well, the first one is x1, so it comes from that one. That first derivative, this first one is an x2, so it comes from the first derivative x2. This first one is x2, so it comes from the first derivative x2. Now we can go and check. Now it's looking at x1. So there the first term has x1, so I derive that, it becomes minus 2. The second term is just a constant. All of those zeros are just 0, but constant becomes nothing. So just minus 2. I'll write it here for the first one, plus 0. Right, then the next one, let's see. So x1, but now I'm looking at x2. Let me see if you guys caught up on this. What would I write? There's no x2. What do I write? What do you think? Yes, 0. Very good. 0, 0. Right, next one. Let's see this one. So you go to the green, x2 is x1, there's no x1, so 0. Then the next one, the last one before we have our Hessian matrix, it's looking at x2. We do have an x2 there. other one's just a constant, but we do have x2. Derive that, it becomes -2. So we can now fill in our Hessian matrix of -2, 0, 0, -2. So Hessian matrix. Then you could purely use Excel. You're more than welcome to use Excel. I'm just going to go and say the determinant is equal to top left times bottom right minus in the middle and then the other 2. So it's going to be a 4. Right, just to make it clear, like that. And then the other 2. So that's a positive 4. So if your determinant of h is not less than 0, then it is not a saddle point. If it was less than 0, it is a saddle point, or the main gradient is a saddle, right? If you are looking at greater than 0, you are going to say not a saddle point. So it could be convex or concave. So we could look for a min or a max, right? Then we check, okay, how do I know what to look for? If, let's say, we wanted to look for something specific, although I told you there could be multiple maximums, multiple minimums, so this is not your definite answer to say it's only concave or convex. But we go and we check the main diagonals. So these, the main diagonals, x1, x1, and x2, x2. So they're both less than 0, meaning they're both negative. So remember, if they're both negative, they're side face, right? Side face. So you're looking at a maximum. Concave. Max. So you have a local maximum. Whether there's more, we don't know, but you have a local max that you can search for. Definitely. Right, we can say that with certainty. Right, so we're ready to go with question 4. That was all they asked for. That one, we proved our point. Now we can go to question 4. All right, so now we go and start from the beginning. So first things first, they give us an initial guess of 1 and 1. So x1 is 1, x2 is 1. Then I go substitute that literally into my function. So I'm going to keep on using brackets. You could have expanded your brackets. Right, so I'm going to keep on using my brackets. Just want to see what they were so that I can write it down. Otherwise, I'm going to have to scroll up and down quite a lot. So let me just quickly write it out for myself on a piece of paper. So let's see. Right. Okay, now I can scroll back down. All right, so we go and we substitute immediately. So we've got minus x1 minus 3. I'll just rewrite it so that you can also see again. So immediately into x1, we substitute 1. Even though they're the same, just make sure you double check which one's x1 and which one is x2, because they're not always going to be just 1 and 1. That's going to be that. Then for x2, it's also a 1. Okay. Then we go and we say inside, okay, you can use your calculator, but it would have been minus 2 squared is 4, minus 4. Then that's going to be 1 minus 2 is minus 1, that gives 1, 4 minus 1 is 3. So our first initial start there, wait, 1 minus 3 is minus 1, minus 2. Minus 2 squared is going to give you 4, minus 4, not plus 4. Sorry, two screens, I would have been talking to myself for probably the next hour. So, thank you, I realized. But, can you hear and see? Is everything fine? Now sharing my screen. Can probably. Oh, is it back? Cool. Thank you. All right. So, let me start again. So, and now continue question 4. All I did was substitute the 0.1 and 1 into the one of the brackets, and I get a z of -5. Minus is perfectly fine. There's nothing wrong with a negative z value. That's just the current function value. And then we want to maximize, so we're hoping that eventually it's going to climb up and up and up. We're hoping. Right? If it doesn't, well, then we have to start somewhere else or search somewhere else. However, I told you for test purposes, you just continue, right? You continue with what you have as the initial guess, and you see if it maybe climbs the right direction later on, right? Okay. Let's see. Okay, let's go. Right, so from there, once you check, you can now actually start with the algorithm. So your first initial step is to go and get your first partial derivatives, which we do already have. So I'm not going to do that again. We have our first partial derivative in terms of x1, which is -2x1 plus 6. And we have our first partial derivative plus 4. All right, guys, please take note. If there was an x1 as well as an x2, that's not a problem. It just means when you substitute, you'll be substituting the value of x1 as well as x2. Right, so don't ask me in a panic after class, like, what do I do? You just substitute. You have the values, you substitute. It's not wrong. Okay, you're not on the wrong path if that happens with the other exercise. Right. So we go on with the. Okay, let's substitute or guess how we substitute on 1 and on 1. So I'm going to get my I value by using the first derivative in terms of x1. So that's going to be -2 times 1 plus 6. So we're going to get -2 plus 6 is 4i. Then our j value comes from the first derivative of the second variable. So that's going to be -2 times x2, which is a 1 plus 4. Then I'm going to give you 2j. What is our gradient in terms of our function? 4i and a positive 2j. Both positive, but yeah. It's not both 0, so yeah, we have a vector. It can climb. So what is this? All right. So setting 1 is taking the initial coordinate, and then you're going to add the step size with the gradient to that in order to actually move. Right. So now 1 and 1. We don't know the step size. but in terms of y, it's a 2. Now I rewrite that by multiplying the h inside. So that's going to be 4h and 2h. And then we can add the top together and the bottom together. So we're going to be left with 1 plus 4h, 1 plus 2h. So like this. So the top is seen as our x value and the bottom seen as our y value, or x1 and x2. Right, same. Now I have it in terms of h, so I'm going to substitute back. So into my function, original function, I substitute into x1, I substitute 1 plus 4h. Into x2, I substitute 1 plus 2h. Right, so I'm going back to my original function, that whole minus x1 minus 3 squared minus x2 minus 2 squared. So I substitute in there. So it's a minus, then x1 I'm going to put in brackets just to make sure there's nothing that needs to be multiplied. So 1 plus 4h, then it was a minus 3 bracket squared minus, then it's going to be x2. I put it in brackets just in case I need to multiply something or square something, but I don't. I'm just saying just in case. That's for x2, then minus 2 and square. Right, so I'm just going to erase this here at the bottom, just saying that I was substituting it back. All right, let's simplify it a bit. Now I see that I don't need to multiply anything, so I can remove my brackets inside. So it's simply just 1 plus 4h minus 3, 1 plus 2h minus 2. I've got some like terms I can sort out because you always do the inside of your brackets first. Brackets first, bottom. So that is 4h, 1 minus 3 is going to be minus 2. And then it's still squared. Minus, and then the next one, 2h, 1 minus 2 is going to be minus 1. Okay, so if there was something to the power of 0, or power of 0, it becomes 1. If there's something to the power of 1, multiply those brackets out right now. Okay. But anything to the power of 2, you don't have to multiply out unless if that's the root you took. You'll see that in the answers that I already gave. But we're going to immediately go and say this is g of h. So I'm going to find the derivative immediately. Right. So derivative, let's start with this one. So you take your power and you multiply it in front. So it becomes minus 2. The brackets stay exactly the same. Subtract 1 from the power. Then you have to multiply it with the derivative of the inside, which is just 4. For the other side, so let me just do that so you can see that matches with that. So if you feel comfortable with this and you know you'll remember, then this is the root to take. Then this one. So multiply power outside. Then be careful not to put a nothing there and then you multiply everything together. No, it's a separate term. It's just separated with a minus. Minus 2. Multiply, bracket stays the same. And then times with the derivative of the inside. Derivative of the inside. Right. Now I can multiply my values already. I can say minus 8 there. That's going to be a minus 4. My brackets are to the power of 1, so I can immediately go and multiply. So minus 8 times 4 is minus 32h. Then minus 8 times minus 2 is plus 16. I hope you heard me emphasize that plus. It's going to be minus 8h and plus 4. Okay, now we can do our like terms. So this one and this one is going to give us minus 40h. Then that one and that one is going to give us plus 20. So our first derivative, so if you went and you multiplied out the brackets and then did the derivative, you have to get the same answer. All right, now we do the whole setting our first derivative equals to 0. So it will be minus 40h plus 20 equals to 0. And we get our h. So minus 20 when you take it over. And then you'll have, I'll write it out just in case. So you'll have minus 20 there. You divide with minus 40 on both sides. And h is going to be a half, positive a half, or 0.5. It is positive, even though I said it's not your only check because it might not necessarily be a correct indication, but it is positive telling me I'm stepping upwards for a max. That is what I want. So it is a good quick check. It's not necessarily going to be upwards depending on the signs in your original function. Okay, but we do have a step size and I can put it back in to get x and y. So there where I started, so let me just highlight it for you in yellow. There where we started by saying x is 1 plus 4h, y or x1. Y or x2 is 1 plus 2h. That's x1 and x2. But now I have h, so I can substitute and actually find the coordinate. So we can actually move to the next coordinate. So I'm going to now go and substitute it in there. So where I had one plus 4h and 1 plus 2h, I substitute my h in there. So it's going to be 1 plus 4 times a half. Work with fractions. You just fill in whatever we ask, but work with fractions. Right? That's going to give us 1 plus 2 is going to give us 3. And then 1 plus 1 is going to give us 2. So we've got our new coordinate, I'm going to say new coord. So we've got a new coordinate to work with. So we can repeat our steps. So let's first substitute into a function to first see what's happening to a function. So that was the minus x1. So x1 is, let me just write it here so that you can see what I'm referring to. So x1 is 3 because the first variable is 3. So that's 3. x2 is a 2. So now you see they're different. And then we use our calculator, of course. Let me just erase it at the bottom. Three minus 3 is 0, so that's going to be 0. Then 3 minus 2 is going to be 0, so we're going to get a 0. Right, so right now our z value is 0. Does that mean I should stop if my z value is 0? Does that mean I should stop? No, perfect. No, I mean, it's only if your gradient is 0 that you stop. Right, so your z is increasing from the one before where it was minus 5, it's now 0, so it is increasing. So we can now say, okay, it's going up. It's great. Right. Okay, but now we go and we say, right, first partial derivative, what was that again for x1? So I'm just rewriting it again. Minus 2x1 plus 6. My first partial derivative for x2 was minus 2x2 plus 4. Now I substitute this new coordinate, 3 and the 2. All right, so just to make it clear, that's x1, that's x2. So I substitute. So to get my I value, I use f of x1, the first variable, minus 2 times 3. To get my j value, I take the second variable. That's now x2, which is a value of 2. So the top would be minus 6 plus 6. Bottom would be minus 4 plus 4. Do I stop now? Yes. So my gradient, my function, when it is 3 and 2, I can say it's 0 plus 0. So all my variables are not going to move, meaning I found my optimal value, which is literally 0. All right, then we solved. We're done. Usually you'll continue, see with the other exercise, it won't just stop, sadly. Okay, so there you'll be continuing quite a while. All right, if we in a test see that it's going to continue quite a while, we'll tell you when to stop, like after which iteration to stop. And I mean, on assessment queue, you have guidance on what to fill in as well. Right, so you'll have your initial step, which is your first iteration, then your next step, second iteration, blah, 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 blah. You build it up like that. All right. So let's see. I'm going to close this so you know you need to do the other 2 questions. It's going to be quite a while. Saying stop after the 6th iteration. So you'll be having your I plus 1, which goes from the initial step. The point is 1 and 1, but then the point will change. Then you'll have your second step, which comes from the first one, and then its own gradient and its own age. Third, da-da-da, fourth, da-da-da, fifth, da-da-da, and you'll go up until the 6th iteration, the 6th step. Right, after, they're saying after, so you still need to do it. So I plus 5, then that gradient and that step size. Right, just to make sure you practice more than enough. Right, I'm going to go back to golden section search. Let us do one of those so that we have some time. Right, let's take one of these. Just want to copy the headings. And the answers are in the Excel sheets, so you can compare there. It's just I want to copy the headings. Where's my headings? And then I don't want to do exercise 1. That's quite just very long. Let's do exercise 3. I'm not going to do all the exercises with you, but I'll do exercise 3 because it has the exponential one there. All right, just want to make sure you guys can see my Excel sheet with my headings. Just want to make sure. Cool, thank you, Caitlin. So we're going to do question 3 there, x minus e to the power of x. They give us an interval between -1 and 3 for our x values. It's just one variable. The variable might repeat, but it's still just x. It's not x and y or x1 and x2. Then they tell us the level of uncertainty is 0.6, meaning if we go less than that, we are happy we're close to the answer. Right, so let me write all of that there on top. I'm going to copy it and paste it from my other stuff. So let me just paste it here and then move this down. Okay. Let me just, there we go. Okay, so this is what we need. Let's see. First iteration 1. Just want to move my tablet so it's easier to type. Okay, so iteration 1. So we start off with what is our interval to start with. So our interval is between -1 and 3. So -1 is our lower and our upper is going to be 3. The distance value that we work with, we first have to find this 0.618 blah, 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 blah. Remind you it's larger. So if you need to see and to round correctly, you make your column wider. Right, otherwise you'll be telling me 0.6. No, that's not it. Right. Okay. All right, so we've got the great value, right? So that is done by doing the square root of 5. Close your bracket, then -1, everything on top in brackets, and then you divide by 2, right? So now we go and we say this distance value is always going to be that 0.61 blah, blah, blah. So we lock it immediately so that if we copy our formulas, it's locked, it doesn't move. Then that's going to be times with upper minus lower. Upper minus lower to get the gap, right? So you can immediately do the gap as well to say upper minus lower to see the gap between them, which it is 4 between them. I mean, -1, 0, 1, 2, 3. There's 4 between them, right? Okay, then to get x1's value, I drew out the picture a few times yesterday. But to get x1's value, you take the lower and you add the distance to get x1. To get the value of x2, you take your upper minus the distance to get x2. So the formulas will stay exactly the same. Just type, don't type, just select, don't type. Right, you want to copy formulas, right? Now we want to do our function. So our function is x minus e to the power of x. So I start with saying it is x, which x1, I'm looking at x1 currently, our first value of x, minus, then I'm going to put brackets. So we'll see if this will work perfectly. Remember, I gave you advice of using your calculator in radians to double check that the values match. Otherwise, you made a mistake on Excel. Right, so that would be Euler value, so e or exponential value. So returns e raised to the power of a given number. Okay, e to the power of a given number. What's the number? X. So I select x1, and then I can close my brackets. Right, so you would go on your calculator and make sure that 1.47, blah, 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 blah. Don't round too quickly, but I mean on your calculator, you're just checking. So it's fine if you round to just check if it gets close enough. So you would go 1.47 minus e to the power of 1.47. And then you check that it's closely the same. If not, then your function or the way you set up this equation on Excel is incorrect, or your brackets are in the wrong places, or something's not fine. Okay. So always have your calculator there to double check. Now from that one, I'm using the exact same function. So I'm going to copy it. So click and drag and double check. Please double check. It's now x2. Yeah, we're happy. Right. Then double check on your calculator just to be sure and safe. Okay, it matches. Great, we can continue. Now, what are we searching for? We're searching for the max. Max. So I'll do the whole max here and say between our function values, we want our z value to go to the max. All right. Then I'm going to create my interval here. It is an interval, so it must go from small to large. And in terms of x values, not z values, x values. I mean, your z value is not on the interval. That's just your final answer of your objective function. So we would go and say, okay, that would be lower. And then if we check between the two, which one's first, it's probably always going to be x2, but you should just double check. And then x upper. Select, don't type. Even if it's a -1 that you can quickly type. Select, because you want to drag your formula down. x2, x1, x upper. Does it go from small to large? Yes, so it makes sense as an interval, and I can start. So you'll see what I normally do is I immediately go and literally copy everything down of while so that I can just change it up for the next iterations. Okay, so iteration 2. So for iteration 2, I need to change my lower and upper, otherwise literally everything stays the same. But what do I change? So now we check. So I'm just going to highlight the iteration we are in. So now we check between them, which one will give me a z value that will go higher. So that's this check that I did. The -1.167, what? That one is bigger. So that one will take me closer. Max. If this was a min, I would then go with the smallest value. But it's a max, so I go with the highest value. Right, so that's going to be my largest value. The x that gives me that larger z value is x2. So x2 becomes my center. So if in order for it to be a center or a middle, you're going to have one below and one above. So the upper falls away. The upper now becomes the value of x1. So here, when you now go to your second iteration, you go and say, okay, the lower, yeah, that stays the -1 there, the one below. But my upper changes to, instead of 3, it changes to this value of 1.47, blah, blah, blah. Right, and there I go. Remember, if you can drag it, you'll see the values are even bigger. So please double check that. Right. All right, so we're ready with the next iteration. So now I'll go with the next one. So now we're here. Is the gap less than this level of uncertainty, 0.6? No, so I need to continue. Okay, lucky for me, I did this, so I can see quickly which one gives me my max. Double check, is it selecting the right stuff? Is this still 0.61, blah, 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 being selected? Is it doing the lower plus d? Is it doing upper minus d? Is it this x1 into the same function? The correct x1, not the previous one. The correct x2, the correct upper minus lower. Right. This is the max one, so it refers to this specific value. So it's again x2 with one below and one upper. So in my next iteration, I now go and say my lower is the same, but my upper changed to 0.52, blah, 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 blah. Right. So now I'm at my next iteration. Okay. Is my gap less than 0.6? No. So I need to continue. Now I look between the two, which one is bigger because it's the max problem, but I did this to check because otherwise negatives are quite horrible to work with. But this one is my max. So now it is x1. Please make sure you make your cells bigger if the values look the same. Because in a lot of cases they will be different, but very slightly. I mean, if you did this, yeah, you will be like, oh, it's the same thing, go with the most left. No, it's not the same. Not at all. All right, so x1 gives us the function that's large, function value that's larger. So x1 becomes our center point, but you'll see it's the value of x1, not the function value, right? Be very careful. You don't want to lose points on small stuff that's making it wrong, but you just selected the wrong stuff, right? So you have to know that's why we're using the interval values, which is not your z value. Okay, so now the next iteration. Now the lower changed. The lower is not -1 anymore. It's now this value, -0.41, blah, blah, blah. Now the upper stays 0.52, blah, blah, blah. All right, so I'm now at this iteration. Now we check, is our gap less than 0.6? No, so we go again. Right, so we go again, we check which one is our max value between the two. Let's just make sure, make this bigger. Okay, so it must be that one. Right, that's x2's value. That gives us that z value. So we're working with the x2 value, which becomes our center point with one below or lower and one upper. So in our next iteration, we now go and change. So we go and say our lower is going to be this value. Our upper is going to be that value. We double check our formulas just in case. Right, we double check these, that you selected the correct stuff just in case. But anyway, now we check which one is going to, oh, we don't have to. So right now our gap is 0.58, blah, 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 which means I've reached my end because they said the level of uncertainty is 0.6. If we don't tell you, then your default, who remembers, what's the default? What's the default? .05, that's the correct one, but 0.05, that's perfect. Remember it as being even the smallest, if I can say it like that. So if you remember 0.5, be like, no, smallest. So it must be something small, 0.05. Reason being is then the gap is so small, it shouldn't be so much of a difference anymore. Right, so here we're saying the gap is small enough for us to conclude. But how do we conclude? So to get our optimal x value, we go and look at our last search area, which is, I'm just going to put it in brackets, this one and this one, to see how big is our last search area. But we're just finding the middle of that. So to find the middle of that, you add the two together. Top part, you just put in brackets to say, first add them together and then divide by 2. So get your x value. Just remember the cells can go bigger. All right. So if you then need to get your optimal Z value, you're going to use your function. So I'm going to copy one of my functions. I'm going to paste it here, and then I'm just going to change to this X value. Right, and then I've got my Z value that is optimal based off of that level of uncertainty, of course. Now I just drew you a graph because, I mean, it's one variable, so you can graph it. So you'll see there, the max is very difficult to see though, but will it show me? So there you'll see it's going to be -1, but yeah, just to show you, between -1.14 and there's a minus, it doesn't show me, -0.5. So it's -1, that gives us the max value, and the Z value, we could have checked what's the Y value there. Let me just see. Yeah, it's close. So our Y value there, if I just show you there, that's -1.14, blah, blah, blah. And there is just -1 on the dot. So we're very close to our Y value, which is our Z value. I mean, f of x is Y equals. So it is our Z value. And then our X value is close to 0. So you'll see here the X is 0.5. Here the X is -0.5. So yeah, our X is on 0 there. Right, just to make it clear that we are close, very, very close, right, if we use that level of uncertainty. But that's it. I hope that helped with this. Obviously, make sure you do the rest as well. You'll see if you want to do powers, you can go and say, you can either use the power function and say, for example, this value to the power of 3, because that was to the power of 3. Or you could have gone something like this. We just say the value cap 3, that means to the power of 3 as well. So you could have done that for powers. Use your functions. If you see something new, look if there's a function for it. Remember I told you pi, we had to use functions instead of trying to type in a round value, and then you get the full value that you can use. So see always if there's a function you can use when trying to type it. All right. Yeah, I think we did more than enough for today. Tomorrow we'll go through then only the last exercises, question 1 and 2 of the steepest ascent and descent. It's going to be quite long, so I'll do a few iterations and then I'll be like, okay, now you know already. And then we'll see if we can do the review. Of course, we'll do some more of these. If not, then we'll do the review. But either or, we'll have something to do practice for the test. Yeah, but for today, I'm sure you have a lot of work, so I'm going to greet you. If you don't have questions, then we'll see you tomorrow.